Good morning, Shelby. Good morning, Karen. How you doing? Good morning, Andrew. Hi. Okay, we've got 8:30. Why don't we get started? Good morning, Psych Stats.
Good morning.
That's pretty good. Who's ready for a weekend? All right. Yeah, it's been a very long week, and I'm sure we're all looking forward to getting some REM on Saturday and Sunday morning. Good for the brain to get REM. To set us up for Monday, what I wanted to do is make sure that we're all clear on what we're going to be doing. First, we'll check in when we're on for Monday, right? You've got your presentation going. Is that right? Gwen? Yeah, all right. Okay, great. That's all right. That's all right. You're probably trying to call this up. The rest of us are going to be doing a TED Ed lesson like we typically do for the Journal Club session. It'll be based on the article that was indicated in the syllabus, but what I'd like to do this time is I actually happen to have a full-length video on that article. So you can read the article if you want, but really the questions are based on the video. The video is entitled Remapping Time Across Space, and the video is shown here. Okay, this is me up in room 505 doing this video. So all the questions are coming from that video, but of course that video is an explanation of that paper. Okay, so I think there's one question on the abstract that's in PubMed, and then everything else is really about the video. So we'll see what it's like to do in this case, it turns out to be another vision science paper like we had last time around, but now it's going to be based on the video rather than on the article. But you can still read the article if you wanted to. It's not required. This video is based on that article. Who's okay with that? Right? Okay, so it's good to get a little bit of variety in our TED Ed Journal Club sessions. This is like a video journal club kind of a thing, and then we'll go off to Gwen's presentation. Okay, very good. So we have lots to do today. I'd like to continue our conversation about correlation. That's what we're doing for this week. We're also going to touch on today this relatively new idea of causal modeling. And causal modeling is not something we've typically done in this class, but you're my pilot group on that. So we'll at least get some introduction to that. And I want to make sure that we set the stage for that because that is based on correlations, and we want to do some more correlational work this morning. So when we were last together, we were out in Excel, and I hope you'll join me in Excel. And we can go out to the problem that we had completed the other day, where we had handed you a formula that you don't have to memorize for the Pearson correlation coefficient, and we computed such things as the SPXY. Okay. So if you go all the way out to the S drive, this is in the resources folder. There's a subfolder called practice sets, and this is the one called Pearson practice set. This is what we did manually the other day. And you remember that we have color-coded answer keys in each case for any one of these. So we can plug away on the practice set itself. And if you ever get stuck, it's one click away. You can click on the answer key. And these are all the steps that we had taken last time around. And you can see each of the values as a phenotype. And then you can also click into any one of those. And you can see that we have a genotype there. So you can see exactly where that particular value came from. And so we've done that a couple times. This was the computation that we did. We learned several Excel commands last time around. One of them was, well, you can tell me, how do we get a correlation going between two of these if we wanted to have Excel tell us about the correlation? It was equals Corel. Okay, why don't we do that? Why don't you join me if you can get anywhere out there, equals Corel. And we put in the two vectors that we need, and we like to call them vectors because we learned about cross products, and we'll be dealing with some cross products again today. So we can do the first column and the second column, and we can get a 0.62 correlation, which is exactly what we had wound up with yesterday when we went through all these manual gyrations of computing the sums of squares and the sums of products and summing those cross products up to get to this particular ratio, numerator over denominator 0.62. Okay, so that was one of the two. Does anybody remember the other command? I think we did it yesterday. There's an equal Corel.
Is it Pearson?
Equals Pearson, right? And it's really the same thing, but just in case, it's nice that they've honored Carl Pearson with that. And these are parametric statistics because you might remember that we had to compute the mean in order to get the sums of squareds, which wound up in the denominator of our equation yesterday. We had to compute the mean to get the square deviations from the mean. We wound up with these two items. We have equals Corel, equals Pearson. Okay? Who's got all of that? All right, why don't we do something just a little bit new relative to yesterday? I don't think we got so far yesterday as to add a scatter plot. So why don't we add some scatter plots here? So this is fairly easy. What we can do is grab the data that we have here, and we'll click on Insert a Scatter Plot. And so I'm going to highlight these two, and I'm even going to include worry and concentration difficulty. And let me make sure everybody is with us. Does everybody have that up and going? Yeah? Is that working for you, Karen? Yeah. Okay. And then we're going to go to Insert, and there's a whole range of, and they call them charts. I wish they would call them graphs. Charts sounds a little bit informal, but they call them charts here. Okay, and we see all different kinds that we could have. Why don't we go with the one that looks like a scatter? Okay, we can click on that. And if you open that menu, there are many different options. Why don't we just try this one? It's the first one in the upper left-hand corner. It looks like a simple scatter plot. I'll slide that over so we can have access simultaneously to our scatter plot and also the raw data. And by a show of hands, how many people have that? Did I lose anybody on that? Okay. So it looks like we're all good on that. I'm going to get rid of some of these bars. I'm going to click on that vertical line and just delete it out. And I think I'll leave the horizontal ones in, at least for the moment. Okay. So that's our scatter plot. And just so you can fully understand how Excel has done the labeling, it seems that the default inside of Excel is to take the first of the two vectors, maybe the more leftward vector, and call that your predictor variable. That's going to be on the x-axis, and then it's going to take the criterion variable as the second one that you've put in. Criterion is what goes on the y-axis. So there's a little bit of terminology there. We have predictor variables, and we have criterion variables. And so sometimes what will happen in some conventions is they'll take the y-axis variable and they'll make that the title of the graph. I actually don't typically like that, but that's what some programs do, and that's what we have going on here. Just so you can see that, in fact, this particular column really is on the y-axis. Why don't we take the very first number, which is a 5, and if you'll click on that 5 with me, and why don't we turn it into a 9 and see if we get some kind of vertical change in at least one of the dots. So I'll do that, and one of the dots shot upward. If I change that 9 back to, with a Control-Z, I can go back to 5. So I'm toggling back and forth between 9 and 5. And you can see that we're getting a vertical change in that particular dot. People following that? Does that work for us? You can play the same game over on the x-axis. Here's a 7 for that same respondent. Why don't I turn that into a 2? I should get now some kind of a leftward shift, and I can Control-Z that and bring it back and forth. Right? So I think it's Control-Z and Control-Y and Control-Z, and I can toggle back and forth just like that. Okay? Now what's interesting is if I change that to we'll go back to a 2 over here. You might see there's a little change over in this number, right? So we get a small change in that. It's hot linked to this entire data set. So we get slight changes in our correlational value depending on each of the items in here. Because it is a parametric test, and parametric tests are based on means, and means are sensitive to every one of the scores. We can come up with a non-parametric equivalent to this, which might be based on medians, and then some fluctuation of any given score probably will have no effect whatsoever on that kind of a correlation. Who's following all that? Working for us? Okay. What I'd also like to show us how to do is how to add at least one bell or whistle to this kind of a graph. And so what we're going to do is insert the r-squared value. So these are r's. Okay. Those are r's. Why don't we manually compute the r-squared here? And when I say manually, we won't go all the way through all of these gyrations, which would be very, very manually. We'll stay right here. We'll just now square this. We'll say equals our upstairs neighbor, raised to the second power, and we get a 0.389. Okay. Can somebody remind us what the r-squared tells us that's different from what the r tells us? You actually had a TED Ed question on it, but you might not recognize that you had a TED Ed question on it. So the r-squared tells us something different from what the r tells us. Yeah, thanks.
Is it how well the data fits to the theory that's proposed?
Okay, it's something like that. How well the data fits to the theory. And by the way, what is the theory being proposed here?
That worry and concentration difficulty are related to each other.
They're related to each other in a particular way?
Well, in much more, there's a positive relationship between.
Okay, looks like a positive relationship. And specifically, the default here is always a linear relationship. Okay, y equals mx plus b would be the notion there. Next week, we're going to take a look at some kinds of correlations that are highly nonlinear, but we're just setting the stage here for linear correlation. So that's a nice way of thinking about it. I like the way that Melanie described that. It tells us something about the strength of the relationship between a model, like a best fitting linear model, and the data. And that is indexed on a scale that goes from what to what? Can you tell me? R-squared would range between what and what? So I'll yell it out. 0 and 1, right? Because if we, because r itself can go from -1 to +1, right? So if you square -1, you wind up flipping that half of the axis over, okay? And so we wind up with +1 on the high end. And of course, if we just had a circular pattern of dots, the best fitting line would be perfectly flat. Okay, we'd have no correlation there. If we square 0, we wind up with 0. So we're going to wind up with some measure of, here's one of the ways of thinking about it, the total amount of variation in the y-axis that can be linearly explained by variation in the x-axis. It's one of the ways of thinking about it. Explained is a strong word. We use that a lot in statistics. I tend not to like explained because it sounds like there's a causal relationship there. And all we've done is computed some sums of squares, some means and deviates and so forth. We haven't really said that there is a causal relationship here. You'd actually need to do some research method-y kinds of things to establish a causal relationship. But we can say that there is a accounting of 39 or 38% of the variation in those y-scores given the x-scores. And that is according to a linear model. Does anybody remember another name for the r-squared? You actually had it for the TED Ed for Wednesday. But I didn't ask you to explicitly link it to r-squared. It was one of the vocabulary words that you learned for Wednesday's TED Ed. I'll give you a hint. It wasn't coefficient of variation. It wasn't coefficient of variation. I remember the other term that you learned? Coefficient of determination. Okay? The coefficient of determination is called the r-squared. Okay? I'm going to float one other mean for you here. Okay? Another way of thinking about r-squared, it's the proportion of variance explained beyond the mean. It sounds like a weird definition, but you might take that down. The proportion of variance explained beyond the mean. So when we have a data set, we can begin to describe a data set using descriptive statistics and typically the 3 measures of central tendency, mode, median, and mean. Okay? If I have a perfectly flat line, I'm not really saying anything. I'm not explaining any more variation beyond what the mean would have explained. The mean would be right in the middle of that set. That line is right in the middle of that set. Okay? But if I get a sloped line, I might be able to account for more of the variation in the y-scores than the mean would alone. Okay? How much more? That's what R squared is telling us. The proportion of variance explained beyond what the mean would have explained. So if we wind up with a 0 here, why bother with this y equals mx plus b, which has 2 parameters? Why not just describe it with 1 parameter, which would have been more parsimonious? Who's following that? Is that working for us? Okay. So when we're doing a correlation, we have to take 2 means. When we're doing regression, as we'll see, we'll have to take 2 parameters, a slope and a y-intercept. Those are 2 parameters. Or we can describe the data set using 1 parameter. How much better are we doing than the mean if we use this correlation, this linear correlation? And the answer is, on a scale that goes from 0 to 1, we're 38% of the way there. Okay, so we're doing a little bit better. Okay, why don't we see if we can get Excel to plop in maybe a line and also a R squared value. Okay? So let's do this. If you'll highlight that graph, okay? And this might take a little bit of clicking around, but once you've got it highlighted, there should be a green plus sign in your upper right-hand corner. If you can see the green plus sign, can you raise your hand? Okay. Takes sometimes a little bit of motor skill here. If we click on that plus sign, we generate a whole lot of possibilities off to the right-hand side. If we go down to trend line, and we click on the arrow to its right, we get this kind of menu sequence, and more options is the one on the bottom. So we went to the green plus sign, trend line, more options. Can you all click on more options? That should generate some sort of a menu for us. Yeah. And you might notice, even doing that much, we've now got a small dotted line that's the best fitting line there. How many people have that? Okay. What I'd like to do is, just for the moment, next week we're going to go crazy with all kinds of nonlinear fits, but we won't do that today. What I would like to do is focus on R squared today, the coefficient of determination, trying to figure out what fraction of the variance are we explaining beyond the mean. We'll say, display that, and as soon as you click on that, you get a 0.3898. I'll put this guy away. And how many people have that? You've got an R squared floating somewhere on there. By the way, I don't always like the way Excel plops that in the middle of nowhere. They sort of take it and they throw it. It would have been nice if they put it up by the title, right? But somehow they didn't do that for us. Okay. So hopefully you'll see that Excel is computing a 3898, and we're getting a 3898 down here after we took a correlation and squared it, either with equals Carrel or equals Pearson. Who's okay with that? Yep, that all works, okay. Now, why don't we do this? Why don't we play around a bit? I'm just eyeballing these scores, and I notice that they seem to range, I don't see any double-digit numbers, so they appear to be integers less than 10. Why don't we make all of these guys turn into random numbers that are between 1 and 9? Okay, so I'm going to go up here on the 7, and can you tell me the random command for getting numbers between 1 and 9? I'll call this equals, and what do I put in? Rand between 1 and 9. I'll do just that one cell for a moment. Okay? And then what you'll see is every time I hit that, I'm driving that poor dot crazy. It's kind of fun to see. But even that little bit is enough to tilt the strength of the correlation, right, where it gets stronger as it's steeping away from 0. Okay? And R squared is changing instantaneously up there and down here as R is changing. Okay? Then when you're set and you're really ready to have a lot of fun, you can drag that guy down, you can drag that guy over, copying the genotype. Right? And because we have our spatial relationships just as they should be, we're getting all kinds of correlations now. And hopefully you can see and you can develop an appreciation for the fact that every once in a while, if you'll stop on a negatively sloping item, you'll get a negative down here, but R squared, of course, is positive, right? And we're not explaining here, in my particular example, we're only explaining 5% of the variance, and that's 5% beyond what the mean would have done for us. Okay? So we have a more complicated model. We have 2 means and all of that computation and that slope and so forth, but we're only buying ourselves 5 additional explanatory points on a score that goes from 0 to 100. Who's all right with all of that? Okay. Any questions on generating a scatter plot in Excel or R squared? Right? Or how to interpret R squared, the coefficient of determination, on a scale from 0 to 1? Okay, while we've got this handy, maybe one other little trick. Every once in a while, you will find that you would like to generate a scatter plot on data sets that are not contiguous. So here, we happen to have a contiguous data set. We have this vector and that vector happen to be right next to each other. But every once in a while, you'll find that they're separated. You've got one vector here, and then there's some vector somewhere else in your Excel spreadsheet. And that happens to be the case if you'll join me by clicking over into the practice set. We typically separate them when we're doing the manual computation so we can get the deviates, the square deviates, and all that jazz. Okay? So let's see if we can do it this way. I believe you can highlight worry. Okay? And then I think the trick is to hold down the control key. Okay, so I've got that down with my left index finger. I'm going to highlight over concentration difficulty. Okay. And then I think I can do insert, and I'll go back to my scatter. Okay. Right. So if you use the control key, you get some freedom in moving that cursor around, and then everything else would be the same. Who's all right with that? That work? Okay. So now we have ways of generating scatter plots, adding some R squares, and adding at least a simple linear fit. Next week we'll do some nonlinear fun and find out how we can improve our predictive power by using nonlinear relations. Okay, just to make sure that we don't get too Excel biased, and we also develop some competencies inside of SPSS. A lot of folks will be doing SPSS for their senior research or other research here in the department. Why don't we open up a tabula rasa inside of SPSS, and we'll do a very quick correlation and a very quick scatter plot. And then we'll come back to some manual computation in Excel. So what I would like to do is create first a correlation and then also a scatter plot inside of SPSS using the same data set that we just had over here in Excel. We'll go back to this one. All right, go back to that. So I don't think this part of the semester, so far in the semester, we've gotten to actually doing any kind of data entry into SPSS. We've always been using the GSS93, which is a nice data set. We actually haven't created our own data files. And I find that when my students have to create their own data files, there's usually a little bump in the road there. That is, they have now memorized what to click on inside of SPSS, and maybe they know what to look for in the output, maybe they don't, but they don't always know how to get the data set going. So if I told you that I'd like you to use SPSS to find a correlation and also generate a scatter plot on this data set, can somebody tell us how we would get that started? That would be a good first step. Create the variables. Thank you, Vanessa. Let's go over to this in SPSS. We want to be on variable view. That's always, I think, the best step is to create your variables. And we'll call one of the variables worry. We'll call the other one concentration difficulty. And remember that SPSS has a rule that you can't have spaces in your variable names. So we'll say here, this one was worry. The other one is concentration. Sometimes it can be advantageous to use all lowercase and then with the start of every new word, make that capital. You don't have to do that. Clearly, it doesn't affect the computation concentration difficulty. Okay. And then if we go over to data view, you can see that we now have two columns ready for some kind of input. Okay. What would be a next step? Just yell it out. All right, just copy and paste. Why don't we do that much? We'll go back over to here, and I'll grab these two. Be careful not to grab the respondent. You want worry and concentration. Okay, then we'll come back over. We'll do a simple copy and paste. What's nice about that is it prevents us from doing any kind of motor error. If I had to copy 10 or 20 numbers down, I almost certainly would make a motor error. Okay? Okay, the two things we wanted here statistically, we wanted a correlation. We also wanted to see the scatter plot. Okay? And can anybody tell us how we get the correlation going? Probably been a while since you used that. It might even have been that since you took research methods, they've rearranged the menus. Sometimes you have to pop around inside of these menus to see where things have gone. Anybody want to take a guess at how we're going to get a correlation out of this? Where's a good first step for almost all of our analyses? Okay, all right. So why don't we go that far? See if anything catches our eye. Correlate, that's a pretty good one, okay? Lots of different kinds of correlations. We'll call this one a bivariate because we have only two variables. Okay, so let's go to correlate bivariate, and we get this. How many people have gotten that far? Yep, okay. And then we can slide these in, I think, in any order. I think that'll be just fine. Okay, slide them in. We could take some options if we wanted to. We can get the means, and we can get cross products and things like that. But those are kind of minor players, given that we really just want to get the correlation. When you're set, you can click on OK. All right, and you get some Pearson numbers, Pearson correlation. Worrying constant here, standard deviations and so forth. I'm going to go back over to my data. And of course, I've used now, I think those were all random data. So it might be that you pasted in some random data. Is that what people have there? Okay. So what I've pasted in is one that, let's just make sure we all know where to pull that out. My Pearson value was minus 0.239. Can we yell out some other Pearson values? What else did people get? 0.32. Did anybody happen to come across a significant correlation? What did you get? Yeah, so what was your correlation value? Yeah. Okay, right. And that sig value was, okay, so she wound up with a sig value that was less than 0.05, right? So we're getting statistical significance right there. Mine is non-significant. It would actually make sense in a group of 20 that about one of us would get it. We're not quite 20 people, but if we were 20, then 1 out of 20 would put us at 5%, right? So we can expect that to happen. It's a fun thing about being in research methods in a room with exactly 20 computers, is that it maps to one student on average getting the 0.05 value. Okay, how might we get some scatter plots? There are probably several ways of getting scatter plots. We'll look at the options for our menus. What's a good choice in the menu across the top here? Graphs looks good, okay. Lots of different ways of doing this. Can I call your attention to legacy dialogues? Okay, because if we do legacy dialogues, there's immediately a scatter, and I'll point to it, and I'll let you go ahead and click on it. That was graphs, legacy dialogues, and then finally a scatter dot. Okay? And graphs is about 2/3 of the way over from left to right. Okay? All the way down, legacy dialogues, scatter dot. Okay? So we'll put that in. And then for now, we'll take a simple scatter plot, and we'll define it. Okay? And we can put concentration difficulty, if we were so inclined, on our y-axis, and worry on the x-axis. You could have flipped that around the other way. You could add a title if you wanted to. I'll just put in my title. Okay. And we'll let it rip when you're ready to go. And mine will not look like yours because we've entered some random numbers here, but Vanessa will have a relatively steep-looking function because she was one of us who wound up with a statistically significant effect. Okay? So anyway, it's a way of getting the scatter plot going if it turns out that your psych advisor is looking for a scatter plot on your data for your senior research. Okay? All right. Questions about any of that? So far, so good. Why don't we put SPSS away for the day? I do want to go back to Excel and open up a different Excel spreadsheet. Can you open up the one that is entitled, got it right here, Practice Problems for R by Z-scores. So we're going to do another manual computation. We'll do this a little bit more quickly because now you're good at it, but we'll show you that you can get to the R statistic a few different ways. This also gives us a reminder about how Z-scores work. So it's good review. It's good manual practice to do this a couple of different times. And we'll see if we can get into this problem number 1, where we're looking at the hours between, the relationship between hours slept and mood. Does everybody have one of the Z handouts? Everybody have one of these? So same, we could do this lots of different ways, right? And we're going to use the Z-score mechanism now. Okay. All right. So if we want Z-scores, what's a good first step to computing a Z-score? A good first step for computing a Z-score? How is a Z-score computed? Well, we have it right in front of us. Right? We've got a bunch of raw scores. What else do we need? We need a mean, okay, right? So why don't we go ahead and do it this way? I'm going to come over here. We'll make this our predictor variable. We're going to see if hours slept is a predictor of mood and to what extent that's the case. So let's put in mean. And I'm going to put mean x, okay? And we'll use equals average. And away we go. Okay? And I wound up with a mean of 8. Who can corroborate 8? All right, we get an amen on 8. Okay, why don't we go ahead and get our deviates for x and our squared deviates for x. You can denote this any way that you want. I'll call it deviate x and squared deviate x, something like that. Okay, is equal to my neighbor to the left minus the mean. And remember that we have to freeze that with this and this. Freeze that and drag it down. We'll square that to get our squared deviate. Oops. Okay. I think that worked. Why don't we come back over to here? Well, let's organize this slightly differently. And we'll see if we can get our sums of squareds for x. So SSX will be equal to the sum. And this is always the sum of the squared deviates. So we've done this kind of thing many, many times. You've already been quizzed on that. I wind up with an SSX of 12. Let me see how many people can corroborate that number. Okay. Some of us are still plugging. That's all right. We'll let you catch up on that. While you're still plugging, I wanted to ask you a question that makes us harken back to something we learned earlier. We had actually 2 different flavors of standard deviation and 2 different flavors of variance that we could compute. Remember that there were 2 different kinds of variances, 2 different kinds of standard deviations. Okay, remember what they were?
Population and sample.
Population and sample, right? Typically, Excel defaults to using a sample. In almost all cases, that's what we want to use. Weirdly, and maybe a little bit counterintuitively, maybe not, in this computation, we actually have to use, if you will, the equivalent of the population. So rather than divide by n minus 1, we're going to divide by n in just a moment here. So we're going to get the variance, and we'll get the variance for x. Typically, if we were doing a sample, we would take the sum squared, we divide by n minus 1. If we're doing the population, we'll divide by n. We're going to simulate the population here. And I'm going to put in here variance x. I'll put parenthetically pop, in case we do one of these on a Excel quiz or a computer quiz, you'll need that to be the population. So what we're going to do is divide by the number of scores that we have, and I'm going to have Excel count for us. Okay? And it turns out that there are 10 scores there. Okay? So that's just the count. What I really need to do is divide my upstairs neighbor equals this guy divided by the count. Okay? And I wind up with a variance, which is actually the population variance of 1.2. 12 divided by 10 is 1.2. How many people follow all that? Is that working for us? Okay. Does anybody remember how we get from a variance to a standard deviation? This will be the standard deviation of x. Again, population style rather than sample style. Okay, yeah, that's a mantra, right? The standard deviation is the square root of the variance. So this is equal to my neighbor upstairs. Actually, the square root of my neighbor upstairs. Okay, 1.09. I'll let you see if you can confirm that number, 1.09 and a lot of change. Who's got that? Okay. All right, so we've got that going. Just so I can demonstrate to you, you don't have to do this with me. If we use the standard deviation command, we'll get a slightly different number than the standard deviation we just computed, equals STDEV. Okay, and that's because, why are we getting a slightly different number? Usually we nail it to many, many digits precision. Go ahead, Melanie.
That's the standard deviation.
The sample, which is dividing by n minus 1. And that's typically what you'd want to do for this particular computation. It's defined as all of the scores in your set. Okay? All right, can we go ahead and why don't we get the z-scores now associated with it? We have a standard deviation, we have a mean. So why don't we call this zx? And you can see I've been in on this Excel spreadsheet because if you're in column E now, it's probably turning red for you. Okay? Right? So we have the z formula also shown in red down here. Okay? So what we're going to do is say equals, and I think it's best to introduce a parenthesis because we are going to do some differencing before we do some dividing. And if we keep the order of operations straight, we'll have to take the raw score. In this case, our first raw score was 7. We're going to subtract from it the mean. Okay, I'll click on that 8, which was B17 for me. And we're going to divide by the standard deviation for that particular set, population style. Okay? And we wind up with something like a negative 0.91287. Who's got that? And I'll pause. That was score minus mean, parenthetically. We're going to take that quantity, and we're going to normalize it by the standard deviation. So that was, if you're playing along by letters, I did B6 minus B17. Here's B6. My mean is B17. Score minus mean divided by my standard deviation with the population. Simply following that little red formula there. Okay? All right. Now I'm going to make at least one error or two errors here. Okay, I've got that, so let me drag it on down. Uh-oh. You tell me. I screwed up because I did what? Or neglected to do what? Okay, and here, just a heads up, we have to freeze two things, because we always want this guy, and we want to freeze it to that mean, and we want to freeze it to that standard deviation. So let me go back in to my initial one, and I'm going to say, yeah, I want the neighbor 2 doors to the left, so we'll leave that one alone, but I also want to freeze it at a constant mean value. So I'm going to freeze the B17 because that's the referent to the mean. In my case, I've got it in B17. And I also want to freeze it to this standard deviation, which is going to be B20. So I'll freeze it to that. I still wind up with the minus 91287, but if I drag that down now, hopefully I've got something a little friendlier. Okay. I'll let you catch up with that. How many people have that? Okay, looks like we're mostly there. I also did one other thing. While I generated those, I clicked on the simple summation here just to check myself. And hopefully this is intuitive. Half of the z-scores should be above a mean, and half of the z-scores should be below the mean. So some are going to be positive, some are going to be negative. If we add the positives and negatives, they should sum up to 0. So just a little z-check. Right? That number came out to be crazy different from 0. Not just some kind of rounding error different from 0, but crazy different from 0. Maybe you have a computational error in there somewhere. So a little check on yourself. Okay? Just to get the practice, can we now do the same thing for the y side? We'll go ahead and do that quickly. Exactly the same steps, but this will be the meany, the mean y, the SSY, the variance for y, and again, that's going to be population style, which we don't typically do, and then the standard deviation, population style. As Melanie pointed out, that's not what Excel normally computes. We'll get the deviations for y, and their squared counterparts. However you'd like to denote that is fine. And I'll let you go ahead. Oops. I'm going to slide that over one so I can put my means in here. Okay, I wound up with a mean of 4 equals my neighbor to the left minus the mean. Freeze it, and you can always freeze it, or if you don't like freezing it, you can add it. You can add a variable name to it. You can call it the mean y, for example. Okay, I'll bring that on down. Got my deviates. I'll square my neighbor. I've got the square deviates. Once I have the square deviates, I can sum those to get the sum of squareds. And I wind up with a sum of squared 30 for my SSY. I'll divide that by my count. It's my upstairs neighbor divided by, I'll use Excel's counting mechanism, equals count. And I wind up with 3. You probably could have done that in your head. I'll take the square root of 3 using Excel's square root function. And wind up with 1.73. Then I'm going to go ahead and do my z-scores now for the y variable. This is what we're trying to predict, our criterion variable. This is mood, and we'll put in zy. Right? And we'll just try to really memorize that formula. Raw score minus mean, and that's going to be parenthetically done. That's my raw score minus the mean. While I'm here, I'm going to freeze that because I know I'm going to need a lot of differencing with the mean. And we'll always normalize that, which is to say divide by the corresponding standard deviation for that data set. And I'm going to freeze that one too, because I'll need to always subtract from that same mean and normalize by that same standard deviation. I'll drag that on down. Oops. And now I've got a list of z-scores. I can take a quick check. Those sum to 0 also. This just as a quick check. So now I have the scores, I have their variances, their standard deviations, I have all the deviates, I have the z-scores as well for each of those. The standard, the raw scores and the standardized scores, which we call z-scores. How many people have that? Okay. Several of us are still plugging. We'll give you a moment to catch up. This isn't a race. You shouldn't feel bad about that. With practice, we do get faster, and I'm sure some of you are already faster than I am at this. Okay, so now it looks like we have lots of the ingredients lying around on our sheet to begin to complete this. Okay, it actually looks like a pretty elegant definition of an R. All we're going to do is take the sum of our zx's by zy's, and then we'll divide that by n, and that should work out to an R value. Okay, so here we're back to getting a cross product. Come over to this L4 cell, and I'm just going to remind us that this is a cross product. This is one of the terms that we learned about in TED-Ed, and I loved how many of you define this. We're going to multiply one vector, which is simply a list of numbers, by another vector in an element-by-element manner. Okay. So we're just going to do the zx by the zy, okay? And I'll even put that in here, zx zy. If you wanted to put a multiplication sign between those two, that's fine. Okay? So I'm going to say this is equal to this one that's over in column E. It's my zx times that same participant's score on the y variable. And of course, I'm multiplying by a 0 here, so I'm going to wind up with 0 in that case. But I've now formatted a spatial relationship, really a cross product. I'll drag that on down. I get lots of numbers there. So I drag it on down. And just by a show of hands, how many people have a cross product? Yeah, okay. Most of us are there. So that's zx times zy. So we have, for any given score, we have this much of the formula. We'll forget about the summation sign just for a moment. We've computed zx for everybody, we computed zy for everybody, then we multiplied those to get the cross product. Okay? It's a fun visual that I've been thinking about in reading your responses to what a cross product is. They talked about having a plane that's defined by 2 dimensions, and then the cross product sticks out in the other dimension. So it's easy. I like to think about it this way. I've got a piece of paper just like this. This is my y-axis. This is my x-axis. If I tilt it over just like that, or if I go like this with my hand, right? Here's the y-axis. Here's the x-axis. I blow it down. It's like that. And then I'm going to get some kind of a cross product and some kind of a list over there that's going to be positively balanced or negatively balanced or perfectly zero. If it's negative, we're going to get a perpendicular line coming down this way. If it's positive, perpendicular line going up that way. If it's zero, we don't get any extent away from this plane all by itself. Right? One of the ways of thinking about that. Why don't we take a simple sum just to complete the numerator here? Right? We're going to take the sum of these cross products. So equals sum. And we'll go up here. And I'll just simply label that sum of zx, zy. Okay. We also want to simply define n, and I think we know intuitively by now what n is, but we'll have Excel do the counting for us so we can practice that count command one more time. Okay. So now we have, again, I promised ratios, ratios, ratios. We have a numerator essentially right over its denominator. Okay. And we'll say equals my numerator divided by my denominator. This is coming right from the formula, right? And wind up with 0.843, and that actually is my R statistic. Okay, so now we've done R statistics using a very different mechanism. We didn't directly use in that formula the SSX or SSY as we did the other day. Okay, and we can do one more check on this. I'll put a check. Okay, and now we'll say equals. Why don't we go with Pearson? Wouldn't really matter which one. And I want to correlate this vector, hours slept, that's what I'm using as my predictor, to predict mood, close that off, and to many, many digits of precision. You can see that it's good to see Excel getting it right. Okay, this is what you did manually, and you're confirming that Excel can actually do their arithmetic correctly. Okay, so now we have a couple of ways of thinking about Carl Pearson's intuitions of finding these deviates, squaring them. We did that in the chi-square world when we were looking at qualitative bits. Now we're doing it over here. We're getting deviations, and we squared them yesterday. We're also getting z-scores, and we can sum up the z-scores and as cross products, and we can wind up with our correlation coefficient. Okay. All right. Who's okay with all of that? Okay? Just as a reminder that one more time, I would encourage you, if you're a little bit unsure about these or you want to develop a little bit of speed, there are many, many practice problems. If you'll join me by clicking out all the way to number 5, number 5, I have a random data set A and I have a random data set B. And if you hold down those numbers, you'll see that you get that random data set. And I think over here on the practice side, we have all of that going on here as well. What I think is most critical, I'll zoom in. If you look at the red and the blue, at the bottom down here, go to 200, and I'll slide over. No matter what random number we use, our red and our blue are going to be equal to each other, right? The check from Excel and our manual computation are doing really well. And they're always tracking each other. Okay? All right. So we're developing some computational savvy, some Excel savvy, which is probably a good one to have when you go out into the real world. Almost all organizations are going to have Excel. Many fewer will have SPSS. Okay? Questions about any of that? Okay, I think that's about as far as we want to go with simple bivariate correlation. So we've done now this linear case of bivariate correlation, and this is an extension of Carl Pearson's earlier work on the qualitative chi-square. Next week, we're going to start to get into nonlinear regression and multiple regression, so simple spins on this. But now we've set the stage, and we've got a really good base for all of that. We also did a little bit of time inside of SPSS to see how that would work. Okay, what I would like to do is have at least a bit of conversation about some of the ideas relating to correlation that we didn't get to the other day. So I'll just call out a TED Ed question, and we'll see if somebody can help us understand this. Thinking still about the topic of simple linear correlation, what we've just been doing. Can somebody explain the idea of range restriction and how it relates to correlation coefficients and the R statistic? Range restriction. Range restriction. I think it's a very, very interesting phenomenon. Okay, thanks.
So it's range restriction is when the range of scores you have is concentrated in one area, like with floor, ceiling, and such. Okay, right. Okay, so you almost brought us into the next one, right? So we have a very small expanse or dispersion on one of the variables. Okay. And that tends to make our correlations quite a bit smaller. Karen also had a hand up. Did you want to add anything to that, or was that basically the whole thing?
I was going to say possible values.
Okay, yeah, sure, right. So you see a very small dispersion on one of the axes that tends to ruin our correlation. So I would like to give this as an example. Did you know that in American football, there's actually no correlation between body weight and one's success as a defensive player, as a defensive lineman? There's actually no correlation there whatsoever. You might find that surprising because these folks really need to be pounding into each other, and you would think that the heavier fellows would, all other things equal, cerebus paribus, have an advantage over those that are slightly lighter. Okay? But there's actually no correlation between your success as a defensive lineman in the NFL and your body weight. Okay? Who's following that? That working for us? So, as I might have told you when we introduced Z-scores a couple of weeks ago, I weigh somewhere between 125 and 130 pounds. So I'm thinking about packing it in as a stats and S&P professor and going off to the Chicago Bears and playing linebacker, right? Because we just established that there's actually no correlation. And you might say, well, aren't you a little bit light to be a linebacker? Right? Linebackers are on the order of like 300 pounds or more, right? I'm at 125. So if you doubled me, I'd still be light for a linebacker. But the claim is that there's no correlation between one's body weight and one's success as a linebacker. So why shouldn't I do that? Well, why shouldn't I pack it in and go play for the Chicago Bears? Aside from the fact that I'm probably too old, yeah. Okay, there's a restricted range of weights. Okay, so maybe 280 really isn't that different from 290, right? Maybe 290 isn't that different from 275. Okay? But 280, 290, 275 are way different from 125. Right? Okay, so it might be that we had something like this. Okay. Here's your success in NFL as a linebacker. And here's your body weight. Okay. And if you could see the full range of scores, it would probably be pretty positively correlated. Okay. Here's me down here at 125. I don't know what this is, maybe 350, right? But it turns out that if you looked at the 250 to 350 range, and that's all you saw in your scatter plot, the best fitting line in this scatter plot is that, right? But the best fitting line in the whole thing is like that. Okay? If you look at only this restricted range, we kill the correlation. If we look at the range in all its glory, we get a very strong correlation. Who's following that? Okay? So sometimes when you come up null on a correlation, it might genuinely be that the variables are unrelated to each other. It may also be that you have a range restriction problem, and that tends to make correlations smaller or closer to zero. It doesn't necessarily make them more positive or more negative. It makes them closer to zero. Okay? Who's all right with that? Okay, so an interesting problem. Okay? One other bit that I thought I'd share with you as a thought exercise. Let's take a relatively extreme case. I'll draw one more scatter plot. Relatively extreme case of range restriction. Now what I'm going to do is give us a bunch of scores on the x-axis, but I'm really going to restrict the y-axis like this. I'll say 0, here's 10, and I'll say this is 5. I'm probably a little higher than 5. So I've got a bunch of scores, different x values. Okay? All of these are exactly 5. Somebody have an idea about what my correlation is going to be? What is my R value here? What is my R? I have a relatively restricted range on my Y because I have a 5, followed by a 5, followed by a... I could have had a 10, a 4, a 3, a 2, a 1, but I've got all 5s. So I have a very restricted range. This time, the range restriction is happening right in there. Instead of having the full Y-axis, I have only 5s. What's my R value? Can you draw in the air the best fitting line? The best fitting line is going to be just like this. All right. And it's actually getting into regression. But what's something about the R value there? What do you think?
Isn't it 0?
Okay, and why do you think it's 0?
Why, I sort of...
There's not much of a slope there. I think you've given a plausible answer, right? I mean, if I had a slope that went like this, you'd give me a positive R. If I had a slope that went like that, you'd give me a negative R. If I have a slope that's 0, you would tell me 0. I think that's very intuitive. Weirdly, that's actually not the correct mathematical answer, but that's a good intuition. Somebody else would say, well, every dot is right on that line. Therefore, the correlation is 1. Weirdly, the answer in this particular case, where it's perfectly restricted and all items are exactly the same, the answer is it's undefined. And I'll tell you why it's undefined. If anybody have an intuition about what the sums of squares for y would be? What's my standard deviation on the y? What's my mean on the y? 5? Okay, there's no variation. So I wind up with a standard deviation of 0, which means I have a sums of squares of 0. You might remember that there's a sums of squares for y in the denominator of your R equation from yesterday. And because there's a 0 in the denominator, you have an undefined equation. And so we actually, the technical mathematical answer is this is undefined. And what's really interesting about that is because Melanie had a good intuition. It's flat, so that should be 0. Every point is right on the line, that should be 1. But it can't simultaneously be 0 and 1, so it's undefined. And we're out of time. All right, we have a defined interval of time, and we are done. So thank you for a good session. Looking forward to what you have to say about the video for Monday. And then we'll move on to Gwen's presentation from there. Okay? Have a great weekend, and thanks for a good week.